welcome.
We have a connection to him. Can you hear us?
I can hear you. Hello, everybody. I hope you can hear me as well.
Wonderful. Yeah, loud and clearly. We also have your slides here. You know, this is a live event, so use the opportunity to get in touch with Professor Elmenreich. We will answer all your questions in the Q&A session following his presentation. The floor is yours, and see you in a bit.
Thank you very much. So the title I have chosen, Applications of Artificial Intelligence in the Smart Grid, is of course far too wide to basically to treat comprehensively in the time of 25 minutes. So basically, what I decided is to give an overview and also to focus a bit more, not on the overall smart grid, because that would be still too wide, but basically going to the consumer end, to the smart home, and look at possibilities there, but still to provide a good overview so that this is what you could expect. Of course, the first question is, when did the smart grid start to be innovative? So we have heard several talks today. In some keynote, it was mentioned that that we are now at the point where we really need to speed up innovation. We need to basically get the energy transition forward, and it basically also transported the sentence that so far smart grid was not innovative. But I would not go so far to say it was not innovative at all, because the energy system has always been extended and improved continuously. And for example, on the picture on this slide here, there is a picture of the MIT network analyzer. So this, at least by today's standard, wouldn't qualify as an AI method today, but it was quite an interesting approach, because due to the complexity of solving the power flow problem, it's very difficult to do all the calculations to get proper estimations of the voltages and power flows in a large, even in a moderately sized system. And so one approach was just to build a small model that simulated the whole thing as an analog system. So basically, it was a rebuilt grid which just scaled down voltages and power values. So quite an interesting idea. And this one was the MIT network analyzer. I think it was studied in the 20s. It was based upon a thesis project in 1924, and it was used until the 50s. So also, yeah, there is a paper about it from the 1930s. So basically, when we are looking at applications of artificial intelligence in the smart grid, I think we should also look back on the things that we build things on. So therefore, I have this little retro theme here on the slide. So the idea is to look at novel ideas, but based on established AI concepts. And in particular, I would like to look into non-intrusive load monitoring and an application of energy trading, but not energy trading on the energy market as we know it, but rather energy trading in the smart home. So let's have a look first on non-intrusive load monitoring. So non-intrusive load monitoring is the idea to monitor devices with a central meter. So you have a system with multiple devices, typically a household or a house, or could be even some larger building or business. And there is a meter. So smart meters have been recently installed widely. So we have the situation already that we have a digital meter that is able to do some measurements. And if we're able to get those measurements frequent enough, then we can use the information from the power draws of the whole system to infer about the power consumptions of different appliances. So that's why non-intrusive load monitoring and load disaggregation are usually used for the same thing, basically for measuring the consumption at a single point and splitting it up to look at the consumption of different appliances. And how is this possible? So most appliances have characteristic consumption patterns. So for example, a fridge has a compressor that needs to run whenever the fridge's temperature is reaching a threshold. Then the compressor is running for some time, and then it's not consuming significant amounts of energy until the next time the compressor runs. And as long as the fridge is not frequently opened or the contents change, then we have a more or less regular pattern that can be identified. An oven, for example, that is turned on to heat to a specific temperature would have a pattern where we see like a block of high power for some time until it's heated up to some target temperature. And then again, we have this on-off, on-off, on-off behavior that is there to keep the target temperature. And so different devices have their different patterns, and it is possible to analyze this in order to get information about the different consumptions. And this is quite interesting because it basically saves us the need for installing meters for each device. And why do we want to do this in the first place? The main idea is an application for energy management. If consumers would know which device consumes how much energy, then they would be more energy aware, and then they would be able to reduce their energy consumption by a significant amount, but probably not significant. So some papers speak about 10%, 12%. There is one about 27%. But if you would install a separate meter for each device, probably you would offset this potential savings already by the consumption and extra effort for installing the meters. So this approach only makes sense if you can do it with a single meter. And that's why this non-intrusive load monitoring is an interesting idea. So how can we solve this problem? Now we are getting into the algorithms and the AI part. So a simple approach would be to model the problem as a knapsack problem. So basically, we know the power for each of the appliances. Then we just look which appliances need to run in order to explain the power that is currently measured. The problems there is that we have really a large search space, so which requires heuristic search. So we already have nice possibility for implementing some AI methods and heuristic search methods. But the larger problem is, or an equally large problem also, is that there are a lot of ambiguous combinations are possible. So you would, due to devices having similar amounts of power, and if you have enough devices, you would not be able to really safely state which devices were running. So still, this works for a low number of devices. This is an approach that works. But you need to have good information about the appliances already in the system, and the results, they can change a lot if there is even a small power change, because the optimum fitting of appliances powers into one power consumption might change with every watt. So this is not a very stable approach. Another approach is to look also on the state of the system the time before. So we would assume that it is rather unlikely that a lot of devices change their state from one moment to the other, but it would be rather a few, or in optimum case, just one device that switches its state from one instant to the next instant. So we can model this with appliances models where we have transitions, and then we can build Markov models out of this, and we are arriving at the vectorial hidden Markov model for modeling a whole household. The problem is we only can observe the last part here, the Y's, so the overall power consumptions. So we need to solve this in order to get the information which devices most likely were running here, which devices most likely have switched here in order to explain the power consumption from one instant to the next instant. Of course, this is a problem since we're talking about real meters here. This is a problem that must also be able to cope with noise. And the approach before was one that did not consider noise at all. So there is, if you're interested in this approach, there is a paper down here linked that shows this and also gives some numbers. When looking at and when evaluating such a NILM algorithm, so there is a nice tool set called NILM decay, which can be used. You can feed it with an appliance set or with a measurement set, and then you can look how the algorithm performs. It's also a great place for applying machine learning methods. Sequence-to-point algorithms work quite well for this problem. But one thing that also influences the result a lot is the appliance set complexity. So if a person tells you, yeah, I have a very good NILM algorithm, it works far better than others, and I have evaluated with a system of, I don't know, 20 devices running that amount of the time, and others have also tested their systems also with 20 devices, similar households, and their results are much worse. This still doesn't mean that the new algorithm is better, because it depends on the type of appliances you have in your system. So the appliance set complexity plays a role here, and we also did some investigations how we could measure appliance set complexities. So basically an appliance set where you have appliances with a power consumption that, when added together, can reproduce the power consumption of another appliance, then we have an ambiguity there, which makes the appliance set more difficult to disaggregate. While if you have an appliance set, or this also not only applies for the overall appliance set, but also for the number of appliances that are running at the time. If the appliances that are currently running are easily disaggregated, then even if there is a high number of them, it makes the problem much easier. So it's also very important to look at the comparability of these algorithms and look at the comparability of data sets. We have done some work there. And we have also suggested a measure of appliance set complexity, where given the aggregated power and also the disaggregated power, because we need to know which appliances we're running, we can state the complexity of this system. So this is one challenge, to come up with an algorithm that works well for different data sets, that works well also for these complex situations. And another interesting field of application is also how we can get towards automatic labeling of appliances events. Because in a practical situation, if you're going to sell this to somebody, they to some people living in a household, so they might not be willing to measure all the devices or look at the label of all the devices and enter this into the database. So there needs some possibility of the system to learn, and also systems change over time. So people are going to get rid of old devices, some devices break, some new devices are bought, the fridge is replaced by a better one. So a system also would need to be able to learn over time and to identify and classify new devices correctly. So this is both a very interesting challenge for applying AI methods in the smart grid or smart home area. And second, it's also a very promising approach, given that we have now smart meters in all homes. And at the moment, apart from using them for the same purpose as we had used the traditional meters before for billing, they are not much used at the moment. And by using an approach like this, this might be an interesting contribution, basically build upon the existing hardware. There's also another idea where all the algorithms that should do the disaggregation run on a very small embedded device like a Raspberry Pi, and do all this analysis at the place where it is installed, which basically addresses privacy concerns, because then you don't need to upload your data to some company, but your data is processed and displayed to you within your home. This is also something we are working on at the moment. Not only what are the best algorithms for doing load disaggregation and nil, but also what are the best suited algorithms to do this on a small device, and also having the Raspberry Pi being able to do this with moderate effort and not having too much power consumption. So this was the first idea. So now let me go forward to the other idea. So this also dates back on a concept of evolutionary design and neural networks. And we have developed a system for designing self-organizing systems with evolutionary design. It's called FREVO. And FREVO operates on simulation of a problem. So you have a simulation and you need to have a fitness value. And based on this fitness value, FREVO tries to come up with a design of a neural network that can solve this problem. And usually we're not looking for a single controller, because for this, usually it's more straightforward just to model the problem, think of an algorithm to solve it, implement this algorithm, and we're fine. But when we are trying to design systems, complex systems, where we have many interacting agents, then it becomes very difficult to design those systems with a top-down approach. Because a top-down approach would mean that I would have a good idea of adding some aspect of an algorithm on one device, how this would play out in the overall system. And we have interactions. So if I increase some value by 1%, it could mean that the overall system changes by much more than 1%, because there might be feedback loops. So this 1% might tip some parts over, and suddenly the system is behaving entirely different. So it is quite difficult to use a top-down design. That's why we are going this other way around, using an evolutionary design and just modeling with a fitness function the goal we would like to have. So unfortunately, it's not only saying, okay, this is the problem we have, please solve it, but we need also to come up with a task description. We need to provide a simulation. Of course, simulations are always based upon some abstraction of a problem. Then we need to define how there is the interaction of agents with each other. Then we need to have an evolvable decision unit and the search algorithm and an objective function. The nice thing with FREVO is that it basically helps us putting all these things step by step together. There are also some pre-made components that can be used, so we don't need to re-implement the neural network or to implement the search algorithm, so everything's there. And this way we can go forward modeling it. And so what did we model with this for the topic of this talk? So we looked into trading between components. So the idea was that the devices within a home, they have some knowledge about the usage patterns, and they probably have a better idea if it is possible to momentarily turn them off or shift their operation to a later date than by doing it top down. So we have devices. Those devices have a fitness function. The fitness function is basically to fulfill their task and satisfy the consumer. The devices have a budget, and the devices are then able to buy energy. Okay, buying energy sounds within a home a little bit odd, because usually we don't have a market. We have like a fixed grid price, right? And it wouldn't make a difference if you run the device right now or later in the evening or during the night, unless you have a tariff that is based on different working hours, and it definitely changes when you are having a local photovoltaic system installed. Because with your local photovoltaic system, you are mostly interested in using the power from the photovoltaic system within your system and not feeding it back. And the device also should rather use the photovoltaic generated power than buying power from the grid. Because the worst case would be photovoltaic system during noon is feeding in all its power, while the devices are then later buying energy back from the grid. But on the other hand, it's not always easy to just switch the time of operation of devices. And therefore, we have implemented this trading system. So, for example, how would we model, I don't know, a water heating system? So the water heating system would have the goal that their customer always has the possibility to get a hot shower anytime. So they have the possibility to heat up their water. They can do it momentarily, or they can do it later, but they cannot wait too long. And they have some local budget, and they are trying to do their job with the minimum available budget that is possible for fulfilling this task. And this we modeled. So we suddenly had devices that tried to bet against each other for getting power for some price now or later. And we have implemented this in a home energy market simulator, where we had these devices. Unfortunately, we did not implement it in a real setting so far, but we have it in a simulation, also in this publication, and there we had then devices optimizing their schedule and basically also optimizing with the big advantage that the power generated from the PV system was locally used. So we basically increase the autonomy of the overall system. So yeah, this is about how we modeled the agent with independent controllers. And the constraints are that they are given a budget per device, and they also have the notion of the importance of the device for the user. Because if a television would decide just to save some bucks to turn itself off now, while there is an interesting, I don't know, an interesting soccer game or whatever interests you is going on, this would be a bad decision. So there also needs to be a notion of importance to the user. So this was the other idea. I guess you have not heard about a trader system within a smart home so far. So I think it's quite a little bit crazy, but also interesting idea. Something you can do with AI for the smart grid. Of course, there are many more possibilities, but my time is running out, so I have to go forward to the final remarks. So just very general, so you can use the AI techniques as a tool, but you can also use them for system design. So in the second example, we had used this tool to generate algorithms that then are deployed. And also for handling a complex system, it's also interesting to employ a self-organizing system. But of course, designing such systems always come with several challenges. So we have a lot of uncertainties in this evolutionary approach, and also both with the NILM and with the second approach, doing verification and simulation in order to really validate that the system is working for sure and that it will work when it's rolled out to hundreds of thousands of households as well. This is something that definitely needs more case studies. So there it becomes difficult. Running a simulation using Python or whatever tool you prefer locally is quickly done, but then getting it out in the field is another thing. Okay. So thank you very much for your attention, and I'm awaiting your questions. If there is still time, I hope I was a little bit too long, I see. I'm sorry for that.
All right, and here we are back. We received a couple of questions, and let me just quickly pull them up. Thank you, by the way, for your presentation. I'm sure there are some people who want to know more. I already suggest those that they get in touch with you directly on our platform, B2Match. First question being, are you open for joint applications in Horizon Europe or Digital Europe grants? If yes, in which areas?
Yes, for sure. So we have some experience with Horizon 2020 projects, and basically in areas relating to smart grid applications. Here we are more on this low voltage end, so smart home consumer side. This would be our strengths, but in general, smart grid, yes, and also on complex systems and swarm systems, where we're also quite strong in our research. So both would be possible for some
smart grid, complex systems, swarm systems.
Yeah.
Maybe the person who asked that question, probably get in touch if you have some concrete suggestions. Is FREVO open for contribution as well?
Yes, we are currently discussing, since FREVO is, so on one thing, so far, everything that was done for FREVO was done in-house with our own workforce, which has the positive thing that we still are able to release it under another license. Currently, it's released under a GPL license, which might be a problem, including some tools that are, for example, under an Apache license. So we are at the moment also in a process where we are going to double license it. And in general, the answer is yes. So it's on GitHub, and we are looking very much forward if there are some contributions.
Maybe you can share the link with us for this FREVO, so we can share it with the audience as well.
Sure.
Yeah, this would be very useful. And just a really quick answer for the last question, 1 or 2 sentences. How do you validate your simulation system? Do you validate it on real data?
Yes, whenever possible, we do this. Of course, systems that are reactive, where the system should react on it, are more difficult in this aspect. But for example, for the NILM approaches, we are using real data. We have done there are some existing measurement sets, and we have also done our own measurement campaigns to get some measurement data, especially from households in southern Austria and northern Italy. Also available as open source, everything.
Wonderful. Thank you very much, Professor Elmenreich from the University of Klagenfurt. You stick around for the meeting requests that you probably receive in the afternoon. The meeting session starts at 2 p.m. Once again, I want to ask everybody to be on time for the meetings that you have already agreed upon and answer pending meeting requests, because people want to talk to you. Thank you, Professor Elmenreich, and hope to see you again soon.
Thank you very much.